All right, let's talk about cylindrical and spherical coordinates. This is section 2.7. Uh, Mostly we're looking for you to kind of understand the cylindrical and spherical and rectangular coordinates and how to move between them. What do I mean by understand? I just mean that you can kind of do the trigonometry required to plot and convert these coordinates from one system to the other. There are formulas for doing that, but I'd also like you to kind of understand the trigonometric um, background or behind the scenes that leads to those formulas. You're going to find that if you're using your trigonometric intuition on these problems, you're going to have more success than if you're just memorizing the formulas. Um, Big idea here is, like polar coordinates are useful in describing two-dimensional mathematical shapes. Um, in 3 dimensions, we have not only the Cartesian coordinate system for describing shapes, for example, the equation of the sphere, x squared plus y squared plus z squared equals r squared. That's a Cartesian equation because x, y, and z are Cartesian coordinates. They're rectangular. There are other kinds of coordinate systems on 3-dimensional space, for example, the spherical coordinate system or the cylindrical coordinate system. Those are the two that we're going to talk about today. In the spherical coordinate system essentially relies on 3 parameters. 3-dimensional space, you're always going to have 3 parameters. Um, but those parameters describe different things. Unlike x, y, and z, x describes a sort of motion along the straight axis, x, y along the y-axis, z along the z-axis. The spherical coordinate system has rho, phi, and theta. Rho is the distance that the point is from the origin of the coordinate system. Theta is sort of where it is in the polar uh, sort of xy plane, and phi is its angle from the North Pole. Um, Cylindrical coordinates are a little simpler. They're really just polar coordinates in the xy plane and then tack on a linear z-axis. Um, Both have their uses. Cylindrical coordinates are good for objects that have cylindrical features to them, and spherical coordinates are, of course, good for objects that have spherical features to them. We want to build some intuition about these coordinate systems and learn to kind of work with the trigonometry associated with these coordinate systems. Let's jump over to the textbook and see what we have in store. Um, so for cylindrical coordinates, again, you have essentially the polar coordinate system in the xy plane. R is the distance from the origin in the xy plane. Theta is the angle that the ray out to the point makes with the positive x-axis. And then just add on z. Just add on a z coordinate and you're done. That's cylindrical coordinates. The conversion formulas are relatively straightforward because you've seen them already. These are how you get from r, theta, and z to x, y, and z. If you have r and theta, you can compute x, you can compute y using the polar coordinate transformations, and z just goes along for the ride. And then the inverse transformations look similar. Um, let's talk about some equations in or surfaces in cylindrical coordinates. So let's look at these 3 examples. Theta equals pi over 4. You're describing the set of points. Remember, this is a membership test. So we're thinking about the set of points, r, theta, and z, where theta is pi over 4. Well, what does that look like? If we go back up to the picture associated with polar coordinates, what that means is we're talking about all the points whose theta coordinate is pi over 4. Well, this actually is pretty close to that situation, so let's pretend that that's what we're looking at here. So any point along this ray will have its theta coordinate pi over 4. And really, any point along the ray above and along a ray below that's parallel to this ray will also have its theta coordinate to be pi over 4. So what you're really talking about is just all of the points above and below this ray. And of course, r could be negative, so we could go back through the origin in this direction. So we're talking about all the points above and below this line through the origin that makes an angle of pi over 4 with in the xy plane. That's a plane, right? It's a plane that is diagonal to both the yz plane and the xz plane, but parallel to them. Let's look at a couple more. R squared plus z squared equals 9. Another useful thing that you should sort of tuck into your brain is that r is equal to the square root of x squared plus y squared. So whenever you see r squared, you're secretly looking at x squared plus y squared. So if you take this equation and you replace r squared with x squared plus y squared, and then you have the additional plus z squared, you see immediately that this is the equation for the sphere of radius 3. Last, and probably most interesting of these three examples, is the polar equation z equals r. So now I'm thinking about a surface whose height z above the xy plane is equal to its distance from the origin in the xy plane. Let's look at that a little bit more closely. So here's a view of three-dimensional space that's useful when you're thinking about polar coordinates. Instead of looking at the xz plane or the yz plane, look at the xy plane in combination down here. So you're looking edge on at the xyz space, and you can't see where the x and y coordinate are. All you're seeing is the xy plane. The distance out here from the origin is the quantity r, right? This measures the distance from the origin in the xy plane. So we're not thinking about the specific x and y axes here. We're just sort of merging them together and looking at them edge on. So the distance from the origin is just represented by r. And in this equation, z equals r, what we're saying is whatever if I'm on this equation, the height above the z-axis is equal to the distance from the z-axis. So that leads me to a point like this. Look at this point, right? The distance from the origin here is 4 squares, and the distance above the xy plane is 4 squares. So this point is going to satisfy this condition that its height above the xy plane is equal to its distance from the z-axis. Well, can you imagine what the collection of all those points looks like? Well, certainly every point along this ray is going to satisfy that condition. R is right, the distance from the origin, so every point along this ray is going to satisfy that condition. And then now if we sort of move back and sort of tilt a little bit away from the xy plane, every point in a circle at that height is going to satisfy this condition because there's no theta in this equation, right? No theta means theta can be anything. So what does the collection of points, a distance r and a height r above the xy plane look like? Well, here's one of them, but theta doesn't matter, so here's all of them. And what you're beginning to see traced out here is the upper part of a cone, a circular cone. Now, if we allow for r to be negative, then in fact we can get the lower part of the cone as well. And this particular equation, z equals r, is a cone. Now, depending on your convention, so just a review here, here's the plane, here's the sphere, and here's the cone. Now, in my opinion, this plane extends indefinitely down below the xy plane, and it extends indefinitely back in the other direction on the other side of the z-axis here. So this plane is infinite in all directions. Here's the sphere. Notice they use that identity, r squared equals x squared plus y squared, to get the equation of the sphere. And finally, here's the cone. And again, some texts restrict r to always be positive, and that adds a little bit of nuance, but this text allows r to be both positive and negative. So we get the upper and lower part of this cone, and we get the front and the back part of this plane. All right, let's continue. Spherical coordinates, a little bit more complicated. So the picture that you want to get into your head for spherical coordinates is these three coordinates, rho, theta, and phi, describe certain ways of getting to a point in three-dimensional space. Rho first says the point is a distance rho from the origin. Theta says if you project this line segment down into the xy plane, it will make an angle theta with the positive x-axis. That's what theta says. And phi says if you take this ray from the origin out to the point, a distance rho, if you take that ray and you look at the angle that it makes with the positive z-axis, then that angle we'll call phi. And together, these three quantities, rho, theta, and phi, are capable of locating any point in three-dimensional space. I'm going to grab a copy of this and bring it into our notes so that I can emphasize a little bit the trigonometric relations that are happening in this figure. All right. So if I know rho is the distance from the origin of this point, I'm going to change over to red, I guess, here. Can you help me figure out r? Now, r is not part of the spherical coordinate system, but it is useful in understanding the trigonometric relationships between x, y, z, rho, theta, and phi. So if we look at r here, notice that it is this distance in this particular right triangle. And it might be more useful to actually look at it up here. This is also the distance r. And we can see that, oh, and let me put the right triangle in there. So this is the right angle. So if I know that this angle is phi and this distance is rho, then I can figure out r by trigonometric work. I know that r is going to be rho times the sine of phi. And we're not interested in this particular distance, but if we were, we would see that this is rho times the cosine of the angle phi. So just basic trigonometry related to that right triangle. So what we've determined is that r is actually rho sine phi. And we can use that. Actually, we are interested in this one. I take it back. We want the z-coordinate, right? Here's the z-coordinate of the point. Rho cosine phi is the z-coordinate. All right. How do we figure out the y and the x-coordinates? Well, let's look at a different right triangle, namely this right triangle. And we now know this distance r. This distance is rho sine phi. So what's this distance down here that's going to correspond to the x value? It's just going to be r cosine theta. So x is r cosine theta. Y is r sine theta. And then, of course, we don't have an r in the spherical coordinate system, so we want to re-express this solely in terms of spherical coordinates, but we can do that because we know that r is equal to rho sine phi. So x is rho sine phi cosine theta, and y is rho sine phi sine theta. And these three formulas together, which I'm going to highlight in green, here, here, and here, give you the transformations that go from spherical coordinates, rho, theta, and phi, to Cartesian coordinates, x, y, and z. That's where these come from. If you do a little bit of trigonometry, you can kind of reverse these and learn the useful identity that rho squared is equal to x squared plus y squared plus z squared. Tan theta is y over x, and less useful, but sometimes helpful, phi is the arc cosine of this. All right, and here are the transformations from cylindrical to spherical and vice versa. So the thing I want you to take away from this is you can always figure these formulas out by building right triangles and thinking about the relationships between the Cartesian coordinates and the spherical and or cylindrical coordinates. Let's look at some spherical coordinates, surfaces, spherical equations. Starting here again with a relatively straightforward one, we have theta is equal to pi over 3. So that, remember, this is a membership test. What are all the points in spherical coordinates that satisfy this condition? Well, rho can be anything, and phi can be anything. So we're looking at theta equals pi over 3. Let's go back to our diagram, and maybe we'll paste another one in there. This is example 265. And let's see if we can't sort of reason out why or what theta equals pi over 3 looks like. I'm going to draw. You know, our intuition just is woefully or hopelessly bound to Cartesian coordinates. So I'm always drawing these things in Cartesian coordinates, even though I'm talking about spherical coordinates. All right, this is the first quadrant over here. So theta is talking about an angle along a ray like this. In fact, let me change colors. So along a ray like this, making an angle pi over 3 here in the first quadrant. Rho can be anything. So if I am a point, think about the plane that kind of extends up above this ray going in the direction pi over 3. Any point on that plane is going to project down onto this ray. And therefore, its theta coordinate is going to be pi over 3. So rho really can be anything, right? The distance from the origin can be anything. And honestly, phi can be anything. As long as I'm on this surface and I'm above this ray making an angle pi over 3, rho can be anything. This is rho. This is rho. And notice also, phi can be anything, because there's no specification about phi. So if you let phi and rho be anything, then what you're really getting is all of this plane. And this plane is cutting across this line that's making an angle pi over 3 through the origin in the xy plane. So theta equals pi over 3 is a plane. What about phi equals 5 pi over 6? Phi equals 5 pi over 6. Once again, I'm going back to the Cartesian coordinate system for my intuition. So I drop in a set of axes. And now I'm talking about any point that makes whose ray through the origin makes an angle of 5 pi over 6. And I guess I should draw it a little bit more true to form here. Get that axis back in there. A little bit more true to form. X, Y, Z, like that. Remember that that angle is from the North Pole, from the positive z-axis, so it's kind of going out like this. Let me change colors. And that's this angle right here, 5 pi over 6, 5 pi over 6. But theta can be anything, and rho can be anything. So I can have points all along here, and they're all going to have that same phi angle. And furthermore, I can go around and through this opposite angle, and all of those points are going to have their phi angles being 5 pi over 6. So what I'm really getting here is a cone. A cone that's opening up along the z-axis, and it's pretty wide. Its interior angle with the z-axis is 5 pi over 6. And we're allowed to have stuff below as well. So this would be kind of, just to draw a little bit better, that dotted line down there is not super good for perspective. Be a cone like that. So every point on that cone has an angle, makes an angle 5 pi over 6 with the positive z-axis. And honestly, yes, I should be careful. We don't get this lower bit here. That's not an angle 5 pi over 6. So we just get the upper part of the cone, not the lower part of the cone. Other surfaces are a little bit more challenging. Let's talk about rho equals 6. Rho equals 6. So this is the collection of points that are a distance 6 from the origin. Well, what is that going to be? Collection of points that are a distance 6 from the origin. Well, let's say that's a distance 6 from the origin. 6 units. Well, if we look at all of the points, right, phi can be anything, theta can be anything. If we look at all of the points, then this is literally the definition of the sphere. It's the collection of points that are 6 units away from the origin. So that's a sphere of radius 6 centered at the origin. You should definitely kind of build your intuition by sort of understanding that this is a plane with angle pi over 3, or whatever the angle is. This is going to be the upper part of a cone, or maybe the lower part of the cone if phi is actually greater than, boy, I really screwed that one up. Let's go back to that 5 pi over 6. This is not 5 pi over 6 either. Let's go back and clean this up. We're talking about 5 pi over 6 from the positive z-axis. That's all the way down below the xy plane. Sorry about that. This angle, 5 pi over 6. All right, and then corresponding on this side, and then that's the cone. So phi equals 5 pi over 6 is the lower part of a circular cone. Like this. Apologies. All right. Let's keep going here. Rho equals sine theta sine phi. Okay, my move here when it gets more complicated is I start staring hard at these coordinate transformation formulas. You'll notice there are some things that look kind of like what we're seeing here. And that's typically how these exercises are going to work. Anything more complicated than that, it's just too hard to kind of figure out what the surface is. So let's see if I can't walk you through that. So we're now talking about a surface described by rho equals sine theta sine phi. Going back up to these formulas, this looks a lot like the y thing, but we're missing the rho. So rho equals sine phi sine theta. I can kind of get to that if I want, just as an experiment. I can multiply both sides by rho, and I'll get rho sine phi sine theta like that, which I immediately recognize as being y. And on the left-hand side, I immediately recognize as x squared plus y squared plus z squared. So now I have the Cartesian equation, x squared plus y squared plus z squared equals y. Now I got to figure out what kind of shape this actually represents. I'm going to move that y over to the left-hand side, and you're going to see that we're looking at a complete the square kind of situation that will help us further figure out what's going on here. X squared just goes along. We have y minus half of the coefficient on y is 1/2 quantity squared. Now, by doing this, we get the y squared minus y, but we've added an extra 1/4, which we have to remove, plus z squared. We can move that 1/4 over to the right-hand side. And now we see we have a sphere of radius 1/2 and center 0, 1/2, 0. Certainly looking at this, we have no intuition about that. But if we do a little bit of manipulation, we go over to Cartesian coordinates where we have a lot of intuition, we can gain insight and figure out that this is what the surface should look like. All right, that's a brief foray into cylindrical and spherical coordinates. There's a bit more discussion at the end about relating spherical coordinates to latitude and longitude positioning on the surface of the Earth. It's interesting, and it's not something that I'm going to focus on right here. We may revisit this later, but if you're doing exercises at the end of the section, you're worried about the assessment, you don't have to focus too much on latitude and longitude. Moving on to the examples, let's look at a few selected examples from the end of the section. In problem 364, what you're being asked to do is find the rectangular coordinates for the given point. I'm going to focus on only the highlighted red ones. These are just exercises I copied in order to get the instructions on the same page as the exercise. So here we're talking about r, theta, and z, and r is 3, theta is pi over 3, and z is 5. So remember, this is the order matters here. This is the first slot is always r, the second slot is always theta, and the third slot is always z. I usually draw an xy plane when I'm trying to figure this stuff out. And I know that my point is a distance 3 from the origin and makes an angle pi over 3. So it's going to be something like this, 3 pi over 3, like that. And now, immediately I see I have a right triangle. I should make this much larger. Let me make this much larger. So the distance from the origin is 3. The angle with the origin, or with the x-axis, is pi over 3. Immediately drop a right triangle, and you're going to be able to figure out x and y. Clearly, x is 3 cosine pi over 3. Cosine of pi over 3 is just 1/2, so x is 3/2. Y is 3 sine pi over 3. Sine of pi over 3 is root 3 over 2, so this is 3 root 3 over 2. And z, remember in cylindrical coordinates, you just tack on the z coordinate. So it's just a 5. 5 goes along for the ride. So in Cartesian coordinates, or rectangular coordinates, this point is 3/2, 3 root 3 over 2, and 5. In problem 370, we're asked to find the cylindrical coordinates given the rectangular coordinates. Let's focus on, again, problem 370. And when I'm working in cylindrical coordinates, because the z-coordinate is so simple, I always just focus on the trigonometry in the xy plane. In this case, we are going back a distance 2 root 2, say here, and we're going up a distance 2 root 2, say here. And we're interested in the angle, and don't forget, it's the angle with the positive x-axis. So what's this angle? Well, we see that, right, since the distance in the xy direction into the second quadrant is equal, we know that to be a 45-degree angle. So this is a 45-degree angle, pi over 4. This is pi over 2. So in total, we're talking about theta is equal to 3 pi over 4, the sum of those two angles. What's the distance from the origin? What's r? Well, we know x, we know y. You use the Pythagorean theorem to figure this out. So we know that this distance is 2 root 2. We know this distance is 2 root 2. Square that and take the square those, add, take the square root. R is equal to, what do you get when you square 2 root 2? You get 4 times 2, 8. Another 4 times 2, 8. Square root, that's 16. 4. So R is 4. And finally Z, just going along for the ride, is 4. So in cylindrical coordinates, this Cartesian set of coordinates would be 4, 3 pi over 4, and 4. In problem 378, you're given the equation of a surface in cylindrical coordinates. You want to find the equation of the surface in rectangular coordinates and then identify and maybe sketch the surface. Let's focus on 378. R equals 3 cosecant theta. Cosecant of theta, let's remind ourselves, that's 1 over sine of theta. You got to have all these trig functions memorized. Same kind of deal here. Look, I'm trying to get from these cylindrical coordinates to Cartesian coordinates. In this situation, many, many times, the conversion equations are going to be your best friend. So go up to the cylindrical conversion equations that are way up here at the top of the section and stare at these a little bit. And you'll notice that the y conversion equation actually has a sine of theta in it. What I tend to do is I go back and I focus on that and I see, can I turn this thing into something that resembles that resembles y equals r sine theta. And I kind of can. If you look at this and you multiply both sides by sine theta, we get r sine theta equals 3. Well, now I know r sine theta is equal to y in Cartesian coordinates. And I get the very simple Cartesian equation, y is equal to 3. This is a plane. You're setting y equal to 3, so it's parallel to the xz plane. And it's situated at y equals 3. So we don't even really need a graphing calculator or anything to visualize this. This one was relatively straightforward. But this is a good strategy in general, right? Whenever you have a complicated situation like this, see if you can use the coordinate transformation formulas to turn it into something recognizable in Cartesian coordinates. In 384, the equation of, I feel like this thing got bigger somehow. Oh well, I'm just going to live with it. Maybe shrink it. Yeah, I can shrink it a little bit. All right, in problem 384, the equation of the surface is given in rectangular coordinates, and you're asked to find the equation of the surface in cylindrical coordinates. Once again, I tend to focus on formulas that are useful or that match what I'm seeing in the expression. And here I'm seeing lots of x squared plus y squareds, which I know correspond to r squareds. So I'm going to replace all of those with r squareds. And I get something that looks like this. Look, you're never going to go wrong if you assume that r is positive in a situation like this. R squared minus 3r plus 2 equals 0. So you might think, I've got to replace that with the absolute value of r, but it's safe in this case to assume that r is positive. This factors r plus 1, not r plus 1, r minus 1, r minus 2 equals 0. And what we get are two conditions. R is equal to 1 or R is equal to 2. Remember, this is a membership test. I keep repeating that. And if I look at a set of cylindrical coordinates, that point will be on this surface if it satisfies the membership test. And the membership test is R equals 1 or R equals 2, and theta and z are anything. Well, what does r equal 1 look like? R equals 1 is a cylinder of radius 1 in the cylindrical space. So a cylinder of radius 1, go up and down like that. Okay, but it could also have its r equal to 2, which corresponds to just another cylinder out a little bit further out. Like this. And together, these two cylinders, the surface of the green cylinder, the surface of the black cylinder, together make up this surface. So staring at this, not at all obvious that this is a pair of nested cylinders, but in fact that's what's happening. Pretty cool. 388. So now you're given a point in spherical coordinates and you're asked to find the rectangular coordinates of that point. Once again, order matters here. This is rho, this is theta, and this is phi. So we're going to use that information and trigonometry to figure out the Cartesian coordinates of this point. Remember, you can use the identities, but I think you'll find it helpful to, at least in these early stages, focus on the trigonometric relationships between these coordinates. So now I'm talking about something that's a distance 3 from the origin. Just kind of arbitrarily put it there. And when I project it down into the xy plane, that line segment makes an angle of theta, in this case pi over 4, with the positive x-axis. And finally, when I look at this line segment, it makes an angle of pi over 6 with the positive z-axis. So again, we have formulas for this, but I think it's helpful to kind of figure out, using trigonometry, what these things look like. All right, I just killed my x-axis. Let's put it back. Okay, this distance right here. This is the x-coordinate. This distance right here. This is the y-coordinate. And then finally, this distance up here. That's the z-coordinate. All right, we know this distance here is 3. We know that this is a right triangle. And so this side length, which corresponds to z, is just 3 cosine pi over 6. 3 cosine pi over 6. The cosine of pi over 6 is root 3 over 2, so this is 3 root 3 over 2. A little bit more complicated. Let's figure out this distance, r. We know that distance r is going to be 3 times the sine of pi over 6, right? Because it corresponds to this distance up here. That's r. I didn't do my perspective correctly here. Let's try to match perspective here. Like that. That distance is r. What's the sine of pi over 6? That's going to be 1/2, so this works out to be 3/2. And so what we know is this distance in here, which I'm going to highlight in red, has length 3/2. All right, and it too is the hypotenuse of yet another right triangle that's lying in the xy plane and has this as its right angle. So we can go one step further and we can figure out that x is equal to 3/2 cosine pi over 4, which is just 3/2 root 2 over 2, and y is going to be 3/2 root 2 over 2 as well, because we know that the sine and cosine are equal there. And in the end, we get 3 root 2 over 4, and 3 root 2 over 4 for x and y, and 3 root 3 over 2 for z. All right, that's the trigonometric approach. I encourage you to work through the trigonometric approach as well as learn how to use the transformation formulas. All right, let's look at problem 396. Here you're given the equation of a surface in spherical coordinates, and you're asked to find the equation of the surface in rectangular coordinates and then identify and graph the surface. In 396, rho is equal to 4 cosecant phi, or 4 times 1 over sine phi. Again, when you're sort of faced with these more sophisticated or complicated equations, I think it does you good to fall back on either the trigonometry or the transformation formulas. Here we have rho sine phi is equal to 4. I'm going to fall back on the trigonometry here a little bit. Rho sine phi equals 4, so what I know is that every point on this surface satisfies this equation. And what does rho sine phi actually look like here? Rho sine phi, remember, if we plot just some generic point in x, y, and z space, and we look at the angle that it makes with the positive z-axis, that's phi. And remember, if we build this this right triangle, that distance, if this, for example, if this distance is rho, then this distance, excuse me, is, sorry, not that distance, this distance is rho sine phi. So that's telling me that whatever this point is, whatever these points are, they are always a distance. They're always a distance 4 from the origin in the xy plane. And in fact, rho sine phi is secretly r in polar coordinates or cylindrical coordinates. So by converting to cylindrical coordinates, we see really quickly what this thing actually is. This is a cylinder along z of radius 4. Of course, we were asked to find the equation of the surface in Cartesian coordinates, but now that we've got r in there, and we know that r is just the square root of x squared plus y squared, then we can very quickly get the form of the equation in Cartesian coordinates. So how did I figure this out? To me, like this sort of jumps out at me as part of the trigonometric relationship that I'm seeing in the spherical coordinate system. And that's kind of what led me down this path. Look for those connections either to the coordinate transformation formulas directly or to these right triangles that are sort of lurking in these coordinate systems all the time. All right, 400. We have the equation of a surface in rectangular coordinates, and we want to find the equation of the surface in spherical coordinates. All right, this is one of the few areas in this chapter that's relatively straightforward. If you're given the equation of a surface in Cartesian coordinates, you can immediately substitute the transformation formulas in for each variable. So what I have here in 400, I see x squared plus y squared plus z squared. Now I could go ahead and substitute, oh, x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. Drop it all in there, start cranking away, doing trig identities, and simplify. Or I could just note, hey, x squared plus y squared plus z squared is actually rho squared, right? And then just put the equation in for z. Z is rho cosine phi equals 0. And I'm done. I have eliminated all of the Cartesian variables. This is all right, so we can simplify this a little bit. If I move the cosine term over to the right-hand side and divide out the rho, taking care to note that rho could be 0, what does rho equal 0 actually represent? It just represents the point at the origin. So just note that the point at the origin is one of the points on this surface, and then carry on. Assume rho is not equal to 0. And divide it out, you get rho minus 4 cosine of phi equals 0. Or put another way, rho is equal to 4 cosine phi. What does that represent? Well, let's think about this a little bit. We've got, honestly, we don't have much intuition about this thing, but we have a lot of intuition about the Cartesian form of this. So in keeping with the exercise, we have converted this equation to spherical coordinates, but this is not really going to help me identify what the surface looks like. Indeed, the Cartesian form is going to help me do that. So we'll use the Cartesian form to identify the surface. And do you kind of recognize what's going to happen there with that? Give us some more space to work with. If we group the x, y's, and z terms together and complete the square, we get x squared plus y squared plus z minus 2 quantity squared. And we have to subtract 4 to make up for that completing the square. And we immediately now see that this is a sphere. The radius is 2, and the center is what? 0, 0, 2. 0, 0, 2. So who knew, right? You stare at that thing and you don't really have any intuition about it, but it turns out that that's just a sphere that's a little bit off from the origin, a couple of units off from the origin. Okay, 413, last problem. Find the most suitable system of coordinates to describe the solids. This is a pretty somewhat subjective process. Here we're looking to describe a solid inside a sphere and outside a cylinder. What's the best way to describe this? What's the best coordinate system? Because of the cylinder, I'm going to say cylindrical coordinates are probably better, but you might say, hey, Schuler, there's a sphere there too. And, you know, you might argue that spherical coordinates could work. I'm going to work it up, assuming cylindrical coordinates work out. I'll leave it to you to kind of figure out the spherical coordinates. And I'm partly doing this because there's a mistake in the answer key, and the answer key uses cylindrical coordinates. If you look at this and you assume that we're just looking in the xy plane, this is a cylinder actually centered at 3/2 and of radius 3/2. So it's a cylinder that's going to, let's see, it's going to go kind of like that. It's going to trace out a circle in the xy plane. And then it's coming up out of the plane and going down into the plane. Because there's no z coordinate, z can be anything. So that's the cylinder. And then you can imagine we've got this sphere of radius 3, so that's going to come in here like this. And again, the sphere is coming up out of the xy plane and dropping down below the xy plane, and it's being intersected by this cylinder. And you're being asked to describe the part of the sphere that lies outside outside of the cylinder. These are the kinds of complicated surfaces that we're going to be working with later in the semester. We're going to be doing integration on surfaces like this and volumes like this. Well, how do we describe this using cylindrical coordinates? Let's convert both of these to cylindrical coordinates. In the first equation, we know that x squared plus y squared is equal to r squared, and z squared just goes along for the ride in cylindrical coordinates. And the interior of the sphere is just all of those points that satisfy this inequality. So r squared plus c squared has to be less than or equal to 9. That's everything inside. How do we describe the interior of the cylinder? This is a little trickier. How do we describe a circle that looks like this? Well, you may remember from polar coordinates, you may not, but this circle has a very concise description. We can write it as r equals 3 cosine theta for theta between pi over 2, minus pi over 2 and pi over 2. All right, now we want to build a condition that puts us outside of this circle, and we don't need to do any conditions on the z coordinates because you know, they're not in the cylinder equation. All right, how are we going to do this? Let's focus on this circle and focus. This is a nice review of polar coordinates. So focusing on this circle, I wonder if I can be a little bit more precise here. Let me try to draw some shapes. Let me draw some axes first of all. And let me see if I can draw a circle. Gosh, let's see if I can do this a little bit better. I think if I hold down the shift key, I can make, maybe not, maybe control key. Let's try control. Nope. All right, I'm just going to stick with that and say that looks pretty circular. Sadly, I made my circle of radius 4 instead of radius 3. Oh, and I don't want to put it here. I want to put it here. All right, you may remember that r3 cosine theta is actually this circle where this distance right here is 3. How do we see that? All right, well, when theta is equal to negative pi over 2, we're kind of pointing in this direction. That's the negative pi over 2 direction. And the cosine of negative pi over 2, of course, is 0, so we're sitting here. When theta is, say, equal to negative pi over 4, we're kind of pointing in this direction. That's the negative pi over 4 direction. And the cosine of negative pi over 4 is just root 2 over 2. So we're kind of sitting out here on the circle, a distance root 2 over 2 from the origin. And then when we get to, say, theta equals 0, well, the cosine of 0 is 1, so we're sitting out here at distance 3 from the origin. So I'll remind you, this is theta equal minus pi over 2. This is theta equal pi over 4, minus pi over 4, and this is theta equal 0. And we can imagine going around to the other side that we get theta equal pi over 4, and finally back around here to theta equal pi over 2. So these 2 points would coincide. Now if I want to stay outside of this circle, I need an inequality, and I'm going to start with the inequality r greater than or equal to 3 cosine theta. This is going to be outside of the circle for the values minus pi over 2, less than or equal to theta, less than or equal to pi over 2. What does that mean, r greater than 3 cosine theta? Well, when you're sitting here and you want r to be bigger than the distance represented by 3 cosine theta, you're talking about everything along this ray greater than. And when you're here, you're talking about everything along this ray. And when you're here, everything along this ray, everything along this ray, and everything along this ray. So if I make this inequality, what I'm doing is sort of shading in all of the right part of the xy plane, the entire right half of the xy plane, but I'm staying outside of that circle. So this is a condition that keeps me outside of the circle, but it only covers the right side of the xy plane. How do I get my hands, how do I describe this side, the left side of the xy plane? Well, on the left-hand side, I'm just going to say r greater than or equal to 0 for theta bigger than pi over 2 and less than or equal to 3 pi over 2. Together, they describe the volume outside of the cylinder. And now we're ready to build a massive membership test. So the membership test that describes the volume that this book is looking for, this exercise is looking for, is these two pieces together with the condition that keeps you inside the sphere, which we described up here. So all together, the volume, I'll switch back to black here, altogether the volume is the set of points r, theta, and z. This is set notation that satisfy the condition. This vertical bar means satisfying the following condition. The first condition is that r squared plus z squared is greater than or equal to 9. The second condition, and I'm going to put an and here, the second condition is that r be greater than or equal to 0 for pi over 2 less than or equal to theta less than or equal to 3 pi over 2. That describes the green part, the left part. And finally, it also needs to, sorry, not also, or it needs to satisfy r greater than or equal to 3 cosine theta for theta between minus pi over 2 and pi over 2. All right, that's the membership test. And it's complicated. It's not just a single equation, it's a collection of conditions. So again, if I'm a point in this volume that I'm interested in, I need to satisfy r squared plus c squared is greater than 9. I'm sorry, not greater than 9, inside, less than or equal to 9. And then further, to stay outside of the cylinder, I need to satisfy either this or this. So suggested exercises, of course, review all of the exercises at the end except with the possible exception of the latitude and longitude problems. When you feel comfortable with the material, jump over to WebWork and do the assessment for Chapter 2, Section 7. Thanks a lot.